Hi, welcome back to another video of Proof Pilot. We are here to talk about proving Fermat's little theorem using abstract algebra. Before we proceed, make sure you hit the like and the subscribe button. It will mean a lot to me. So, this is Fermat's little theorem. For every integer a and every prime p, a to the power of p mod p equals to a mod p. Now, I'm just going to make an example to understand what this little theorem is about. So, for example, take a equal to 2 and take p 7, then 2 to the power of 7 mod p will be equal to 2 mod p. And you can easily check that out. 2 to the power of 7 is equal to 128 mod 7 is equal to, let's just do that calculation real quick. And we get 2 at the end as the remainder. So this theorem works right here. We are going to prove that for all of p and a's that satisfy this theorem. And the way we are going to prove this theorem is using abstract algebra. First, you need a basic knowledge about group theory, nothing advanced, just the basics. And we actually need Lagrange's theorem, which is about the order of the subgroup in group. I will just state that, I don't prove that. Then we are going to see some corollaries and prove them. Then we are going to prove this theorem right here. So this is Lagrange's theorem, and I'm just going to state it. I'm not going to prove it because it takes a whole another video to prove this theorem right here. I just make an example so you could understand it. If G is a finite group and H is a subgroup of G, then the order of H divides the order of G. And an easy example for that is to consider the group of Z6 under addition. This equals to, the member are equal to this, and an easy subgroup of this group right here is the subgroup 0 and 3. This satisfies all of the properties of a subgroup, and as you can see, this has 2 members and our original group has 6 members, and 2 divides 6. So this is the first corollary. The order of A, which belongs to G, divides the order of group G. Complete statement is right here. In a finite group, the order of each element of the group divides the order of the group. To prove that, we just need to remember that the order of an element in our group is actually equal to the order of the group generated by that element in our group. So, and we knew that this right here is a subgroup of G. We just said that order of subgroup G divides the group G, so this equation right here holds, and that's the proof of our first corollary. So this is the next corollary. Groups of prime order are cyclic. The way we're going to prove that is really easy. Just consider Lagrange's theorem. We just said that the order of our subgroup divides the order of our group. And since our group's order is a prime number, then h's order can only be 1 or p. This means that h is only the trivial subgroup or the group itself. So that's our next corollary. So this is our final corollary, and it states that a to the power of the order of G or group is equal to the identity member, and obviously A is in our group. The way we're going to prove this is just substituting the order of G by the order of A multiplied by something. We just proved this statement right here in our previous corollary. So now if I rewrite this expression right here, it will be a to the power of a multiplied by something. Then this will be e to the power of something, and this is just e, the identity member. So we are back to Fermat's little theorem. I state it again: for every integer a and every prime p, a to the power of p mod p is equal to a mod p. The way we are going to prove that is using division algorithm. By division algorithm, we can rewrite a as pm plus r, which r is smaller than p and is equal or greater than 0. And if we consider the case that r is equal to 0, then the result will be trivial, so r is non-zero. And here we are going to use another group called UP. This is a group that consists of members 1 to p minus 1, and the operation between these members is multiplication. And you can check that if this is a group. In fact, this is a group. I just want you to check this. So let's say that R is a member of UP. Then by our corollaries, we know that R to the power of the order of UP will be the identity member, and this right here is just p minus 1. So r to the power of p minus 1 is equal to the identity member. Just multiply both sides by r, then you get r to the power of p is equal to r. And since this group UP acts like the mod operation with mod respect to p, then this is actually true. So our theorem is proved. I hope you've enjoyed watching this video, and don't forget to subscribe and follow for more videos.